because it is still a cool topic. We're sort of getting toward the end of virtual memory. So we started talking about extending this concept. So instead of just having virtual memory as a thing in DRAM, that's kind of cool. In fact, that's kind of what your cell phone does, because you still have processes on your cell phone if you have a smartphone, and you do need to have isolation and protections and so forth. But it doesn't have a disk, so it doesn't really have the same notion of being a cache for some kind of secondary external storage that's way slower than DRAM. And so with mobile phones, we sort of stopped there, but on general purpose desktop computers and laptops and so forth, we extend this concept to be a cache of data on disk, which is really neat. We added various things to the page table entries so we could keep track of this stuff. So we have the valid bit now, and we also talked about permissions, read, write, and which is kind of interesting, because you could imagine having a situation where you have a writable page but not a it's not readable. Kind of doesn't make very much sense. And as I mentioned on assignment 8, that's why most of the time when you set permissions on memory ranges using mmap, when you say write, it implies read, but not every system does this, so it's a little bit weird. But at least the way that IA32's page table entries are designed, you can only say read only or read write. So that's kind of the thing there. Now you say your CPU performs address translation. So yeah, this is just sort of, like I said, this is where the rubber meets the road in the most obvious way in operating systems. And that's why it's neat. It's quite a sophisticated system and very, very powerful. And next lecture, we're actually going to spend a little bit of time talking about some of the cool stuff that operating systems do with the mechanisms we're talking about here. Because even though we can say stuff is read-only, that doesn't mean that we only ever use it to protect constant data. There's way more clever things we can do with that than just protect constant data. And so we'll talk about one of those examples next time. It's called copy on write, which is pretty much exactly like the name sounds. When somebody tries to write to it, you make a copy so that you have the original, and it doesn't look like it changes, but it, from the perspective of the process thinks it's allowed to change it whatever it wants, but you just sort of silently make a copy in the background. So we'll talk about some of that next time. Let's see. So we have all these features that we've been talking about. Address space isolation we've had for several lectures now, so it's not that exciting. Context switches are fast. We've also talked about that. That's also not super exciting anymore. It is cool, though, I have to say. And we can share memory regions between processes. So this is kind of a nifty thing now. We haven't talked about this too much. This also happens to make forking really fast. And we'll talk about forking a lot more next time. But this was one of the things that initially was a challenge for computer designers and operating system implementers. Because fork, you have the Unix fork concept where you copy the process. You actually had to copy the whole context, and it was slow. And so people didn't like to fork processes very much. Now it's super fast with our virtual memory abstraction. We can memory map disk files into virtual memory. So this is really nice, because instead of having to manually treat program loading in a separate special way, now we can just memory map those virtual pages, and they'll be loaded in as their reference. This is called demand loading. We don't really talk about that in this class, but when I only load the pages of my program as I need them, then that's demand loading, and the same thing with my heap. I say, you know what, I'm going to set aside 64 megabytes of heap for you, but I'm not going to assign any pages to it. I will only allow you to use pages as you reference them. And so again, that's demand paging. So it's pretty cool technique. Let's see, permissions on memory pages. So that is also really, we rely on this heavily in assignment 8 for being able to control permissions to do clever things. So that's kind of a big theme that underlies assignment 8. Okay, so we'll talk a little bit about Pentium family processors. We talked about the address spaces already being 32 bits. We talked about pages and page table entries and how there's a 2-level hierarchy of page tables in IA32. So pages are 4 kilobytes. That'll become a really important number as we go through this. So identified by the topmost 20 bits, because we have a 32-bit address space. The low 12 bits are just the offset within the page. And we have a 2-level page table hierarchy where the top level is the page directory. Each entry refers to a separate page table. And you might say, well, that seems complicated. And we talked about the reason why we need to do this in the last lecture, because we talked about how the page table, if you just had a single level for this kind of design, would be 4 megabytes per page table, and that's large and that's expensive. That's assuming that the entire virtual address space will be mapped to stuff. Like, we need an entry for all of them. So this is a sparse representation, a sparser representation, I should say. And if we have a whole page table that would just be unmapped, then we just have a null for the page directory entry, and we say it's not valid. And so that allows us to exclude large regions of the address space very easily. Okay, so processes have their own page directories so that we can easily specify each process's address space. And I mean, again, I can't kind of emphasize this too heavily, that when you have one process, it sort of has a certain perspective of what physical memory looks like. That's its virtual to physical address mapping. And when we switch to another process, the hardware really does say, okay, we're completely ignoring the previous process's view of memory, and now we're switching to the new process's view of memory. And so that becomes the view of memory that the processor sees. So it's a really clever thing. And even inside the kernel, like when you make that read system call or you make a fork system call or whatever, the kernel sees that address mapping as well. So it really does become the address mapping while that process is running. And when we switch to another one, that process's address mapping becomes reality. So it's kind of a really neat, clever mechanism. And we talked about page directory, sort of the start of the page table. And we used to call it the page table base register because we just had a single level, but now we're going to call it the page directory base register. That's what IA32 calls it. And I think I was right in my earlier guess that it's control register 3. There's like 6 really important control registers on the Intel processor. And if you try to write to this, you're only allowed to do it in kernel mode. So if you try to do this in user mode, your program will explode. And you'll, well, that's probably what the OS will do to it, but you could also trap that and just ignore it. So anyway, that's the idea here. Okay, so this is the use of the other bits, and I think we talked about this a little bit, but the least significant bit is whether or not the page is actually mapped. So is it present in DRAM or is it not present in DRAM? And if the present bit is 0, the rest of the bits are basically up for grabs. They can be used by the operating system to figure out where might this thing be stored. Okay? So the way to think about this is the OS can come in here and put a special value saying this is an unmapped page. Maybe the value is 0. That would be a really good choice. Or it can store some information saying where to find this page in the swap file. Okay? So Linux has a way of specifying multiple swap devices. I think you can use either files or partitions, and so part of the bits are devoted to that, and then the rest of the bits are devoted to saying this is the actual swap slot in that swap device. Okay, Windows has another way of doing it. It's just whatever the OS wants to do, it can design it. And I think I figured out that, like, since you have 2 to the 31 bits, and you have, you know, it has to point to a single 4 kilobyte page, it works out to, like, you can have up to 8 terabytes of swap storage. That's a lot of memory that you can assign to processes. Nobody goes there, I think. But that's a lot of space that you can have for swap. Okay, when the present bit is 1, then all of these things mean stuff to the processor. So now the processor, because remember the MMU is going to be using these bits for stuff. So present is 1, now all these other bits have a meaning to the processor. That's the page directory entry. Yeah, and I have the page table entry as well. And you'll notice that they look very, very similar. So bits 12 through 31 on both are a reference to something. Okay, so page base address in the page table entry, that's the physical page number that you just plop the offset next to, and then that's what the MMU sends out to the processor. On the page directory entry, that is the page table entry to refer to. And remember that the page table entry is a page in size. So that's why we just have the page number. We don't have the full thing. We only need to have 20 bits to represent that. Okay. So we have all the other bits for other things, and you'll know present is 1 for one of those bits, but then we have all these other bits as well. Let's see. So so I guess these are the common bits. You see that bits 1 and 2 basically allow you to say whether or not this thing is accessible and by whom and for what. So we have read-write, And if we set it to 1, we're allowed to write to it and read from it. If it's 0, then we're only allowed to read from it. We're not allowed to write to it. And then we have user supervisor. So if it's 1, then the user can access it. If it's 0, then only the supervisor can access it. So basically, this allows us to have that separation between user space, which is what user mode programs can access, and kernel space, which is what kernel mode programs can access. Okay? Did everybody understand that distinction? I talked about that a lot last time, so I don't want to belabor it too much. Let's see, other permissions. Yeah, is there something that's like notably absent from these permissions that we have so far? Should be pretty obvious. It'd be really nice to be able to say, you're not allowed to execute data in this page. Because then you could prevent a whole category of exploits from occurring on your hardware, right? And so that's something that's absent here. It turns out that this has been added later on. But you can imagine if you have a buffer that you're using to receive data from a web client, and they happen to try to be naughty and overflow a buffer and put a no-op slide in there and then some code that you want to execute, and they try to target the stack or some function pointer or something like that. If you're like, yeah, you know what, the processor is actually not even allowed to execute any code in that memory region that I store the page in or the data from the client in, then I don't even have to think about it. It's not even a problem anymore. So I can start really constraining what clients are able to do that would compromise my system. So that's kind of a really nice permission to have. It turns out that the way that they decided to add this in IA32 and x86-64 is not in the page table entries, because I think they kind of said, we don't want to control it at that level, because you're probably going to have much more than 1 page's worth of data to execute or not to execute. So at the page directory level, they say, you can't execute any code in this region that the page directory entry refers to, as opposed to just controlling it on a page table level. Okay. Let's see, 3 and 4 are interesting. You have CD, which is cache disable. Okay, so you can actually disable caching for certain parts of your address space. And then you also have WT, which says, do I want to be write through or write back? Do I want to perform every write immediately, or do I want to cache them up and store them? Why would this be a good idea or a bad idea? Actually, I shouldn't even ask. Why would it be a good idea to provide this facility on the processor? Yes? So that's an interesting thought. What would be the most optimal behavior? I think you can basically say, and this is going to be a giant hint, if memory is the thing sitting at the address, then caching will be the most optimal thing to do. Are there any double E's here? Yeah, so you probably would guess this. If you have something other than memory sitting at the address, then caching could start to interfere with that. Some of you may have done that. If you yes.
You can have peripherals attached that aren't that, like, for instance, you can have a display at memory.
Yes.
You want that to be written immediately.
Yes, that's a really good example. Because, when I did 5X, we would have things like the blasted UART that you're using to do serial port communication or whatever, things like that. And but a display is a really tremendous example, because you'll have video memory, and it might make sense that when you're writing to that video memory, you'd like to have caching. I know this is a naive thought, but you'd like to have caching because that way your writes to video memory would be fast. But the problem is you don't actually see the data that you're writing to video memory until it hits the video memory, and the video card can access it. So that is a tremendous example. I hadn't thought of that one. But yeah, so sometimes you want to make sure that the data actually hits the thing you're writing it to immediately. And when you read from it, you actually see the data immediately as well. Okay, so that's why we might want to disable caching for certain regions of memory. Okay, the one that I was mentioning is if you have memory map ports or something like that on a device where you read from an address and it activates the device itself instead of being backed by memory. And so you might read port values off of something, and obviously, every time you read it, you want to actually read the value that the peripheral is providing, not just whatever was cached, which would be terrible. It would be absolutely terrible. So there's sometimes situations like this where we want to be able to say, yeah, this region of memory is not normal. And so it's not backed by normal DRAM main memory where we want to actually do this kind of stuff. I mean, you can imagine another situation as well, like if you're using certain buffer regions for DMA data transfer or something like that, and you want to disable caching for those as well. Okay, but this is the idea. Sometimes I need to actually perform the read or the write every single time, so let's disable caching for that address range. Okay, questions, comments? That's a pretty neat thing. Let's see, access bit. Bits 5 and 6 are like my favorite. Bit 5 is set by the MMU when you have an access that falls within a particular page. Okay? So you have the MMU setting the bit because it knows the access is performed, and you have the operating system kernel clearing the bit. Similarly, you have the dirty bit. The MMU will set bit 6 when you have an access that writes to a page, because now the page in memory may need to be written back to whatever it is a cache for. You have memory mapped IO, or memory mapped files, something like that. You write to the page, now you need to make sure that gets written back to the file. So these two things basically allow you to be very clever in your page replacement policy implementations. You can tell, oh, I'm evicting a page, but it's not dirty, so I don't need to save it anywhere. I can just throw it out. I can replace it with the contents of the new virtual page that I'm mapping into this thing. Okay? So that's one nice thing. You can actually use the dirty bit to tell when you need to write stuff back. The other thing is the access bit basically allows you to decide what pages have been accessed recently. And so, as assignment 8 has, what you can do is you can have a periodic timer interrupt. And in that timer interrupt, you can go clear all the access bits of all the pages in your process. And then what happens is the MMU goes and starts setting access bits of pages that are accessed. And so you can go the next timer interrupt and look and see which ones have their access bit set. If it doesn't, then you know it hasn't been accessed recently. So you can make a decision. There's a lot of really clever techniques for doing this. I mean, that was kind of one of the things on assignment 8 that I didn't want to get carried away with, that I have you guys basically implement 2 page replacement policies. I could probably give you 4 that are all pretty easy to implement, and you'd get to see how they behave in different scenarios. But, I mean, at some point it's just overkill. But we talk about a lot of different page replacement policies in 124, because there turn out to be some really clever things that you can do with these 2 bits to decide what pages to keep and which ones you want to get rid of. Okay, yeah, the processor will cause faults. So if you have a memory access, and again, this is generated by the MMU, because the MMU is the thing that looks at page table entries and page directory entries. If the MMU is trying to map the address and it sees the present bit as 0, then it raises a page fault. Okay, so this is a special kind of fault. It's a hardware interrupt that's generated by the processor. The kernel registers a handler for it, and it can go in and decide how to handle it. Okay, like I say here, it can decide to load it. If it knows that this is a page that's stored on disk somewhere, it can just load it in. Or if it knows that it's unallocated, then it can generate an error and then pass that to the process and perhaps terminate the process. Now, you also have the possibility that the access is to a valid mapped page, but the permissions might not allow it. So you have a situation, maybe you're trying to do a write to a read-only page, or your user space and you're trying to, your user mode, and you're trying to access a kernel space page. Well, in those cases, you get a second fault that's generated. It's called a general protection fault. They're different at the hardware level. The reason why I mentioned that they're different at the hardware level is that they actually both map to a segmentation fault in Unix. There's a way of telling them apart, which is what you have to do on assignment 8. But at the hardware level, they are both, they're different interrupts that generate. Okay, we'll revisit that in a second. So like I say, your page directory and page table is stored in DRAM. And so we mentioned this before, that it's not in a special magical area that's instant access or anything like that. It's in memory as well, so it's slow. So the CPU has translation look-aside buffers that it uses to try to minimize the lookup penalties. And so on IA32, we have 4-way set associative caches like you say here, 16 cache sets. Four-way set associative. Okay, you know what? I'm not going to think about this too much. You can go back and look at that yourself later. But anyway, the translation look-aside buffer has a very simple job. Takes a virtual page number, hands back the page table entry. It's kind of a little bit specialized compared to the hardware caches where we take an address and we give you the block of the data that it has. So in this case, we give you a page number, and out comes the page table entry for that page number. So very, very small, because our page table entries, of course, are 32 bits. This is basically how it looks, conceptually at least. So the processor sends out the access. This is from the program, whatever the program says. Virtual address, remember that 4K pages, we have 12 bits that are just offset, so they go straight into the physical address. And then we have the virtual page number, which is used, hopefully, against the translation look-aside buffer to figure out what the page table entry is. Because that's really ultimately what we need. We need the page number from the page table entry, we need the permissions, and then we can resolve the memory access. And so we have this machinery for handling various situations, which we'll describe momentarily. So I mentioned that there's 16 cache sets. So we have 4 bits for the set index that are taken. Now remember that we're using the top 20 bits to access this translation look-aside buffer. So 20 bits minus the 4 bits for the set index. And so we have 16 bits left over for the tag that tells us if this page is actually in our translation look-aside buffer. Okay? This is all basically the hardware caching stuff we've already talked about. What's unusual about this is that since we have a 2-level page table hierarchy, well, do you know what's better than 2 memory accesses for doing address translation? Less than 2 accesses. So 1 access is better, and 0 accesses is even better. So the way that this cache is designed is that if we can get a partial hit where we see that the tag is in there and we see the page directory entry for the tag, but we don't have the page table entry for the tag, then at least we can use the page directory entry. We don't have to look that up. So that's called a partial TLB hit. Okay, so TLB miss. Okay, like I was saying before, virtual page number is, we take the offset straight through. The virtual page number is broken into 2 values. If we have just a flat out miss, we don't have anything in the cache, then we use the first part to look up in the page directory. We use the second part to look up in the page table. That gives us our physical page number. And then those 2 values, the page directory entry and the page table entry, go back into the translation look-aside buffer. Because ideally, next access will have a TLB hit. Okay, TLB hit, virtual page number broken into the tag and cache set index. So we look in our translation look-aside buffer, we find it, and we can just pull out the page table entry. Okay, we're done. That's the easy one. And that's going to be really fast. Partial TLB hit, basically in this situation we notice that the page directory entry corresponds to the page number that we're trying to access. And so we pull out that, but the page table entry doesn't match, so we can't use that. We have to do the second half of this miss stuff down here. You can see page directory entry comes down. We use that with virtual page number 2 to look up in the page table what is the physical address that we care about and what are the permission bits. Okay, does that make sense? We're not going to talk about this in any more detail than this. It's important to be aware that translation look-aside buffers exist. This is why address translation can be fast enough to actually be useful. But there's certain subtleties about how this works that are they really complicate things. And I'm not interested in getting into that level of grudge. I mean, if you have to design this stuff, then you have to get into it. But as far as a programmer, programming this hardware, is just important to know that it's there. And obviously it affects decisions about laying out processes and so forth, but not as heavily as you might think. Okay, so we have now, we've talked about the hardware a little bit. We also have the kernel, which has to handle situations where we have page faults, protection faults, and so forth. The hardware is going to involve the kernel. So let's talk a little bit about what the kernel does to be able to do this stuff. So we're going to go through a little bit of that right now. Yeah, so processes have their own virtual address spaces, blah, blah, blah. And only the kernel can change the page directory being used, so we already talked about that. This is generally the layout of the process, at least on 32 bits. And we've already talked about this. We've already seen this kind of picture before, but now we got a whole bunch more detail than we ever had before. For example, you can see that there's this magical boundary at C0000000, above which is kernel space, and below which is user space. Now this is 32-bit. On 64-bit, this is a different picture. Okay, but at least on 32-bit, you can see that the kernel reserves 1 gig of the virtual address range to itself, and then the bottom 3 gigs are available for user processes to use. Also, that's on Linux. Windows actually, I think it actually divides it evenly, so the kernel gets 2 gigs of the address space, and the application gets 2 gigs. But there's a way of configuring that on Windows. But Linux, at least 32-bit Linux, just says 3 gigs and 1 gig. So you have various things that fall in here. You can see that there's various addresses that are important in the layout of the program. Okay, like where shared libraries generally start, where the stack generally starts, and so forth. And obviously what direction they go. So I already talked about that. The kernel information is very interesting and cool, and obviously we spent a lot of time talking about it at 124. But you see that we have the kernel stack in the kernel space. Every process has its own kernel stack. It's not very large. It doesn't really have to be large because we don't have nearly the depth of calls in the kernel that we do in user applications. Why? I mean, the kernel needs to be really fast and do very little. So we don't have very deep call sequence in the kernel. Also, when you trap into the kernel stack is where the user process's context is stored. So the kernel stack needs to have a little bit of space for storing the context details, but not a whole lot. Okay, what else? We have things like the page table, the page directory are stored in that area as well. Okay, so we have some things like that. Let's see. Oh, yeah. And so the other thing that I want to mention here is like the global data. The kind of thing that would be in the kernel's global data would be like all processes, scheduling details, so that the kernel can make easy decisions about switching between processes. Okay? So that's the kind of thing that's global data. But we also have kernel code, and I'm going to talk a little bit about that right now. Basically, the fact that we map kernel code into every process makes it really easy to do system calls. Okay? So we already talked about int80. That one was really easy. And the thing that I mentioned before when we talked about interrupts is there's a lot of steps. We have to go look up the descriptor. And the reason why there's a lot of steps is because it's a general purpose mechanism. We can go from any protection level to any other protection level. And if we're going up, then we have to do these privilege checks and so forth and possibly change. I mean, well, regardless of what direction we're going, we have to change the stack if the protection level changes. So there's a lot of slow stuff here. And so i32 added, and I mentioned that Intel added one set of instructions and AMD added the other set of instructions. We have sysenter, sysexit, syscall, and sysret. Those are pairs. Okay? And these are basically, like I say here, fast system call operations. Basically what you're saying is I'm making sort of a wormhole from the user program to the kernel. And I always go from protection level 3 to protection level 0, and I hard code in all of the, like where's the kernel stack, all of this kind of stuff. It's all configured so that this transition is as fast as possible. And so it's a special way of trapping into the kernel. And you can see that using this requires that you have kernel code mapped in the user process. That's why you may say, well, why in the world, if I'm in the user process, would I have a way of saying part of the address space is kernel access only? Well, this is the reason why, so that we can actually have the trap handler mapped into the process address space so that we can jump to it, so we can transfer to it. But we have to do that through a special mechanism, because it is a trap. Okay? In this case, it's okay that it's a trap. Any questions? All right. Let's see, process-specific structures managed by the kernel, only accessible by the kernel. You definitely don't want programs messing with their kernel stacks. That would just be a recipe for disaster. You definitely don't want programs directly manipulating their page tables. Because if you think about it, if I can manipulate my page table, then I can view anybody else's stuff that's loaded into memory. So the kernel reserves all of that. And there's a few other things, the memory mapping info, which we'll be talking about in a second. What files does the process have open? Where's my standard input? Where's my standard output? That kind of stuff is also stored on a per process basis. Okay, so are there any questions about this at this point? Okay, so we're going to start talking about, we have page tables, page directories, and you think, okay, that's awesome. The only thing is that not every processor stores the same virtual memory details. They all have the same basics, but they don't all have the same details. And so, especially if you have something like Linux that tries to support a lot of different hardware, we have to keep additional information so that we can handle differences in hardware, but also so that we can just be clever and do some really cool stuff. So this is now going to be talking a little bit about what the kernel stores. So like I say here, we have data structures that basically track the virtual memory regions that have been allocated to a process. This is separate from the page table stuff. You can see that the struct, so these are the things that are actually used in Linux. So task struct describes a thread in a process. So Linux actually has a representation of threads in processes so that they can schedule on a thread per thread basis. So you have struct, which has PGD and mmap. PGD, if you can't guess, is the page directory. So that's the process's page directory. And then mmap is the kernel's description of the memory mapping. So they actually correspond very closely. Okay. So you can see that PGD is like the stuff that the hardware uses. And mmap is a higher level description with more sort of a higher level, more conceptual representation of what's going on. You have things like VM start, VM end that says this is a memory region. Protections, so VM prot. And if you've looked at mmap now for assignment 8, that's where the protection bits would be stored. Flags, so you can say the various details about, is this copy on write? Is it private? Is it shared? Blah, blah, blah. And then you have a pointer to the next one. So these are linked together in a linked list, an ordered linked list. And they basically completely describe the process's virtual memory layout. All right, so we already spent a lot of time talking about this. Read-write permissions, various other things you can say. You can also say execute, which may be ignored. Okay, so it's not necessary that all of these different protection bits will be valid. And then flags. Another detail, of course, that will be in the VM area struct. You can see that I have a little gap there between VM flags and VM next. I'm only describing the most essential stuff. It turns out that another thing that's in there is this memory mapped? Is it a memory map file? If so, what is the file and what's the offset? So that it knows how to manage that section of the virtual memory region. Okay? It all should be pretty obvious. Now the kernel has a page directory for the process, and it also has this data structure. This data structure is not referenced in normal operation. Because if you think about it, the processor sees move whatever to here. You try to read a value off the stack. You're trying to read the pixel color off the stack into a register so you can store it into your little screen thing for the midterm. Okay? So it's got an address, and that goes through the MMU. The MMU does the lookup. It doesn't want to involve any other software because that would be really slow. So in normal operation, we have page hits, TLB hits. Well, actually, the TLB doesn't matter. Even if it's a miss, the hardware can resolve it. But all of it goes through without touching any of the kernel data structures or kernel code at all. That's awesome. That's like the fast case. The CPU handles it. The MMU handles it. No big whoop. Now, when we have a fault, the unusual thing that you have to recognize is that we have many different causes of faults, and some of them are okay, some of them are not okay. And the issue is that the operating system, the abstraction that the operating system presents is too sophisticated for the details that we can store in the page directory. That's the issue. So the operating system provides more sophisticated abstractions than the hardware support. So we have to keep this additional information so that we can figure out how to resolve it. So, and like I said, we'll talk about some of that stuff next time, because you'll see how these faults can be used in very clever ways to resolve things and provide some very useful techniques. So the kernel has to handle the situation. So you could have invalid accesses. You can see some of these things are invalid. So like writing to the program text, probably shouldn't allow it. Writing to constants that are in read-only memory, probably shouldn't allow it. So we can have invalid accesses. We need to resolve those somehow. We have valid accesses. So for example, I have an access to the data segment because I'm looking at the heap, or I have an access to the stack. One of the things that's interesting about the stack is you think about it's growing downward, right? We start at some address and it's growing downward. And so it's the operating system does the same thing with the stack that it does with the heap. It says this is the address range for it, but at some point when the stack grows far enough, you hit a new page that maybe hasn't been assigned to the process yet, and you get a page fault. And so the kernel's got to say, oh, I've got to extend the stack. It has to extend the pages for the stack so that the stack can grow. So you have things like that that the operating system has to handle. You have to implement that in 124. It's kind of cool. I don't know. The students don't think it's cool during the time, but it's really neat stuff. Okay, so basically the kernel has to resolve all of these things and figure out what is the scenario and how am I supposed to handle it. So that's where the VM area structs become very helpful. So if I have an access and it's outside, then obviously the MMU is going to see that the present bit is 0, so it'll fault into the kernel, and the kernel will look, it basically will scan through the VM area structs and say, this address doesn't correspond to anything in this process's address space. Therefore, it's invalid. So that's how it tells. Okay? Does it fall within some VM start and VM end? If not, then it says, all right, that's an invalid access. I'm just going to go ahead and send a seg fault to the process. Okay? And that's the one, like on Linux, you get the segmentation fault, and if you get the signal information using the sig action mechanism to actually get that sig info, you'll see, oh, this is a map error because it was an access. It doesn't fall within the process's memory mapping. Okay? Now, we could have the situation that it's valid. So what happens here? We don't get the page fault. We get a protection fault. Okay, that's what the hardware generates. The MMU does the translation. The translation is all right, but then it looks in the page table entry, and it says, these bits are wrong for the access. So I have to flag a protection fault now. So, again, the kernel can go and look and say, why did I get a protection fault? Because we have this mechanism, which we'll talk about next time, copy on write, where I basically can have a section that I want to share, but I don't want people to see each other's edits. The easy way of doing that is to make it read-only, and if somebody tries to write to it, you get a protection fault, and you just make a copy behind the scenes. And you change the mapping so that when the fault handler returns, it actually goes to a different physical page, but it's a page that can be written now. So that's called private copy on write. So we can implement that stuff very easily by storing the appropriate information in our VM area structs. So anyway, but either way, it's still reported as a seg fault. I should be a little bit careful because on Macs it's reported as a bus error, which is another reason why we can't run Homework 8's code on the Mac, but you can run it on Linux. They're all reported as seg faults. Okay. But anyway, the default would be for a process to be terminated. Are there any questions about this? Okay. You'll get really familiar with this stuff pretty quick, I think. So it's not very complicated, but the way that I always describe operating systems, the only thing that makes operating systems complicated is the concurrency aspect of it. Everything else it's just a glorified bookkeeper. But the concurrency is the part that makes them challenging. So this is just bookkeeping. Okay, so if we have those two scenarios that have not occurred, we're in some fault handler, and like I say here, the address is valid, the operation is allowed, so we'll be in the page fault handler, not the protection fault handler, because we already know that the protections are allowed. We haven't made our model more sophisticated yet. So we have an access that's valid. The operation is allowed, but it's just a page that hasn't been swapped into DRAM. So we just do the normal page load operations. What physical page are we going to load it into? We try to pick one that's not been used recently, using some mechanism. Using those access bits or whatever, we'd say, hey, you haven't been accessed for like half a second. You're out, or something like that. So it picks a page and evicts it. We load the requested page into memory, and obviously change the mapping to say this is where the physical, this is the physical page frame in which the virtual page is loaded. And so once that's all done, it returns from the fault handler. The CPU retries that instruction, and ideally now it goes through. Okay. Has anybody tried running the Homework 8 code yet? That's another question. But I'm like not edited it yet, but just tried running it. You have? Did you see what it does? Yeah, it infinite loops, which is really cool. I think it's awesome. Because basically what happens is the processor is generating a page fault. It's going into your segfault handler because the kernel passes it on to your process. Your segfault handler does nothing to resolve the fault. So then you return from the segfault handler, and the CPU returns and reschedules your process, and it retries the same instruction. It still hasn't been resolved. So you get another segfault. And so you basically sit in this. That's one of the more fun kinds of infinite loops you can have in operating systems. The best kind is the reboot infinite loop, where you don't know what to do. But anyway, that's the reason why the assignment 8 code behaves the way that it does initially, because the faults aren't resolved yet. But you can see here that when the CPU, or I should say the kernel, resolves the issue, then the fault handler returns, faulting instructions retried, and everything works fine. Okay? Let's see. So oh wow, look at it. It's only 11:47. The thing about next lecture is that the next topic is just too large to cover in the amount of time that we would have. So what we'll do next time is go ahead and finish up our virtual memory coverage, and then I think there's like a special for funsies topic at the end of next class, and we'll just take it from there. So I'll see you all next time.